So, when you look at pictures of natural geysers and areas on fault lines, there is lots of thermal energy present. The water sprays way up into the air and there is steam all around and even boiling mud. So why doesn't the world run on just geothermal energy? Well, at other times we've talked about resource quality and efficiency, but to really maximize the potential of geothermal energy, we need to improve the technologies involved in extracting the energy from the geothermal resource. We also need to find ways around the economic challenges associated with geothermal energy, but we'll come to these later. So, what kinds of technological improvements could make a difference? Well, for starters, we need to improve drilling technologies for geothermal systems because currently we're using technologies developed specifically for extracting oil and gas. Drilling improvements would include better ways to deal with hard rock, the ability to make larger diameter boreholes, and the ability to drill deeper wells. The ability to drill deeper is particularly important as it allows us not only to access more geothermal sites, but also to create more enhanced geothermal sites. At the moment, enhanced geothermal does exist, but it's only at small scale. But it is seen as one of the key ways to maximize the potential of geothermal energy in the future. We also need to come up with more sophisticated geoscience mapping of the potential systems, as well as better modeling of what happens underground in the geothermal reservoirs so we can better predict their behavior with time. We can also look at improving the power cycle used to convert the geothermal energy into electricity. One idea being investigated to get the most out of the power cycle is the carbon dioxide geothermal siphon. Here, carbon dioxide is used as the working fluid instead of water to extract heat from a geothermal resource. For this technology, carbon dioxide is injected into wells, heated by the geothermal source, and then it is used to turn the turbine generator. The carbon dioxide geothermal siphon works on a Brayton cycle, and the carbon dioxide is heated and pressurized until it becomes a supercritical fluid. A supercritical fluid has properties of both a gas and a liquid. But importantly, as we can see on the temperature enthalpy diagram, the power cycle never goes through a phase change like we would see for steam. This means that there is no phase change during injection into the well or during expansion through the turbine. Supercritical carbon dioxide has lower viscosity than water, which means it flows easily with less friction and is able to penetrate the geothermal reservoir more easily than water. This improves the efficiency of our system. Also, because supercritical fluids are very dense, the turbine used on the surface can be much smaller and potentially cheaper than it would be if a steam cycle was used. So, there are lots of technology avenues to explore with geothermal energy into the future. But what about the economic challenges that I mentioned earlier? Geothermal projects are currently very costly. Most of the cost is incurred at the start of the project, as the wells are drilled and the power plant and transmission infrastructure are built. As you can imagine, enhanced geothermal is even more expensive because it requires additional drilling and infrastructure. Future improvements in technology to bring costs down are expected to come from improved design and stimulation of geothermal resources, advances in materials, and improved operation and maintenance. Geothermal energy currently plays a relatively limited role in mitigation of carbon emissions on a global scale compared to other renewable technologies, and this limited role will continue into the future. There is a long history of successful use of geothermal energy in many parts of the world, but at the current rate of growth, it will not form a significant part of the world's energy mix.